Hey, this is Mr. Ariel with the Part 1 screencast for atomic bonding. Today we're going to learn a lot more about atoms, but especially about how they combine. Let's go ahead and get started. Now on this slide, I don't think you really need to write anything down. This is just review. I wanted to remind you that in a previous lesson, we knew that atoms are made out of positively charged protons, neutrons that have no charge, and then negatively charged electrons. The protons and neutrons are found together in the nucleus, and the electrons revolve around the nucleus in a region called the electron cloud. Now my atom is neutral here, so it has 3 electrons to balance out those 3 protons in the nucleus. But I think you already knew all of that, so let's move on. Now we learned in a previous unit that the electron cloud is actually quite structured. I mean that the electrons are arranged in specific energy levels and orbitals. Let's take neon for example. It has 18 electrons, and so its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So if I were to draw those electrons into the energy levels, this first energy level has 2 electrons, and the second level has 8 electrons, and the third energy level also has 8 electrons. Now the thing is, for just about everything else we learned this year, none of these interior electrons are really going to matter for much of anything. Like, we really won't have to worry about them at all. It's just these outermost electrons that matter. Let's move on with the notes. We're getting to a place where you need to start writing some of this down. Now I said you needed to start taking notes, but truthfully, hold on for a second because I'm going to do a lot of writing on the screen, and then I'll change some of it as we go, and then you'll just need to record the notes after I finish the example. I'll remind you when to pick up your pencil. Now let me bring in 3 atom diagrams. I'm going to say that this is hydrogen right here, this is nitrogen, and then sodium is going to be over here. Now looking at the periodic table, I've got hydrogen as atomic number 1, nitrogen as atomic number 7, and then sodium is atomic number 11. Now in a previous unit, we learned an atom's atomic number tells you how many protons it has, but it also tells you the number of electrons, assuming that the atom is neutral. So this means hydrogen would have 1 electron, and so I put that on the first energy level because it can hold up to 2 electrons. Nitrogen is atomic number 7, so the first 2 electrons are going to go on that first energy level, and then there'll be 5 more on that second energy level. Now for the last one, we've got sodium, and that has 11 electrons because it's atomic number 11. So 2 electrons go on the first level, and then that next level can hold up to 8, and I definitely have that many. And so 2 plus 8 makes 10, and so I have 1 single electron left to put on the third energy level. Now an important idea for your notes is the idea of valence electrons. Valence electrons are just the electrons that are found on an atom's outermost energy level. So over here there is 1 electron on the outermost level, and so that's 1 valence electron. I use E with a minus to stand for electron. Over here on nitrogen, that had 7 total electrons, but it only has 5 valence electrons, because those are the ones on the outermost level. And then sodium over here, well, it has 11 total electrons, but it only has 1 valence electron. Now one more idea for this slide is the electron dot diagram. The definition is right up at the top of the screen. These are diagrams that show the element symbol surrounded by dots for each of the valence electrons. So I could draw that in for hydrogen. I just put the symbol, and then I'm going to put a single dot right above it. Truthfully, it wouldn't matter if you put it on the left, the right, or the bottom. I can draw one in for nitrogen, and it's got 5 valence electrons, and so I'll draw them just like this. 1, 2, 3, 4, and 5. It is a little bit easier to count if you pair them up like I did. If you draw them in a circle, it's technically not wrong, but it's a lot harder to count, especially if you're trying to deal with are there 7 or 8 valence electrons. You pretty much have to stop and count each one. Now last up for my electron dot diagrams, here's sodium, and it's going to have a single dot for that 1 valence electron. Now for your notes on this, I'd be sure to get the definitions of both concepts, but I think you need to copy in this entire example from the board, as knowing what valence electrons are and being able to figure out how many there are and how to draw an electron dot diagram. Those are all crucial skills for several units down the road in this class. Pause the video, get all this in your notes, and come back when you're ready. Now, an important thing to note about the shape of the periodic table is that elements in the same group always have the same number of valence electrons. Like on the previous example, hydrogen had 1 valence electron, and so did sodium. So their electron dot diagrams look pretty much the same as each other. Now, drawing out all the energy levels or writing out the entire electron configuration for larger elements is time-consuming. So let's get this idea into your notes, that the ones digit of the group number is equal to the number of valence electrons. In other words, elements in group 1 have 1 valence electron. I'm going to use VE. Group 2 elements have 2 valence electrons. Group 13, well, they have 3 valence electrons, and so on. Now, if you're smart, you'll go to your periodic table and definitely make a note about the number of valence electrons for each of these groups. But the rule only works for groups 1 and 2, and then 13 through 18. So what about groups 3 through 12? Those are the transition metals. And so I'm going to pick out 2 as an example. Here's scandium right here, and its electron configuration would be written like this. It's got 21 electrons, and so that last electron is in the 3d sublevel. But remember that valence electrons are defined as the outermost electrons, and so scandium actually only has 2 valence electrons, because the D1 here is back on the 3rd energy level. Let me take another example. I'll take titanium. I'm going to write it right here. Its electron configuration goes like this, ending on 3d2, but just like scandium, it has 2 valence electrons. So most of the transition metals have 2 valence electrons because everything past the s block is being added to the d block, but that is always 1 energy level inside of that outermost level. Make sure you've got all this in your notes, and let's go ahead and move on. Now, we need to get into how atoms bond with each other. First up, some elements do not bond with anything. Those are the noble gases in group 18. They're over on the right-hand side of the periodic table. They have a full outer energy level already, and usually that's 8 valence electrons, except for helium only has 2 valence electrons, but that's full because that first energy level can only hold 2. Because that energy level is full, helium behaves like the other noble gases and simply doesn't react or bond with anything. Now, an important idea to add to your notes here is the octet rule. Simply put, atoms form compounds in ways that each atom will tend to achieve the configuration of a noble gas. Get that idea into your notes, and let's move on. Now, atoms bond together in 3 different ways, depending on what happens with their electrons. The first type of bond we're going to look at today is an ionic bond. Now, I'm not putting the definition on the board just yet. Just follow with me for a few minutes, and I'll remind you when it's time to come back and summarize for the notes. Now, normally, an atom has exactly as many electrons as it has protons. Like oxygen here, it's atomic number 8 on the periodic table, and so we know that it has 8 protons. Now, all atoms have a neutral charge, meaning that they have no charge at all. And for that to be true, there would have to be 8 electrons. It's kind of like if you had positive 8 minus 8 electrons because they're negative. That would work out to be an overall charge of 0. Now remember that stable atoms have a full outer energy level, so let's see if oxygen has a full outer level. I'm going to use the fast way to know this. You should already have this in your notes. Oxygen is in group 16, and so everybody in that group has 6 valence electrons. I'm going to draw them in just like this. I'm going to write in the electron configuration. That would be 1s2, 2s2, 2p4. And so the electrons here, that's 6 valence electrons. Now, 6 valence electrons means that the outer level is not full, and so we'd call oxygen unstable at that point. Now, if oxygen could gain 2 more electrons, that would make it stable. Doing the math on that, oxygen would still have 8 protons because it's oxygen, but if it somehow got 10 electrons, I'll put the minus sign, that would work out to be a charge of -2. Notice we're calling it an ion now because those are atoms that have gained or lost electrons. Now, if I redraw my picture, if we've gained 2 more electrons, here are the 6 original valence electrons, I'm going to draw the new ones in red. And if I write out the electron configuration, that's 1s2, 2s2, it kind of starts out the same, but it's going to end not with 2p4, it's going to end with 2p6. And so now this ion has 8 valence electrons. And that's the idea of the octet rule, that most atoms will bond to form a stable octet of valence electrons. I think I said in the notes that they tend to form the same electron configuration as a noble gas, but if you look at the periodic table, this electron configuration is the exact same configuration as neon, and that's a noble gas. Now back to that word ion, those are atoms that have gained or lost electrons. And there are 2 types of ions, and they depend on whether the atom has gained or lost electrons. Anion is the name for an atom that has gained electrons and becomes negatively charged. I remember that like an acronym, A negative ion is an anion. Now this is a good spot to pause the video and copy down the information so far that you need into your notes. I'm going to add some more to the table, but you can see the empty spots to draw in so you'll have room in your own notes. Come back when you're ready and we'll move on to the next section. Now moving on, this oxygen right here gained 2 electrons. But let's see what happens when atoms lose electrons. I'm going to use magnesium as my example, and it's atomic number 12, so it has 12 protons. And if it's regular magnesium, not an ion, it would also have 12 electrons, and so that would work out to be an overall charge of 0. Now I need to draw in the electron dot diagram for magnesium, and I can certainly do that the fast way because it's in group 2. It would have 2 valence electrons, but I'm also going to do it kind of the slower way, where I'm going to take the 12 electrons and just put them around in energy levels by counting from the innermost to the outermost. So here are 8 more, and then my last 2 are going to go right here. So magnesium right now does not have a stable octet, but it can become an ion of magnesium simply by losing those 2 outer electrons. I mean, we can just get rid of these 2 right here. So magnesium would still have 12 protons, but only 10 electrons now, and if I subtract those off, that works out to be a charge of 2. Now I want to write out the original electron configuration of magnesium. That was 1s2, 2s2, 2p6, 3s2. But when we lost these 2 electrons right here, that means we lost this part of the electron configuration is gone now. And so by losing those 2 electrons, this part of the electron configuration is the same as neon. In other words, these 8 electrons right here are a stable octet. Now magnesium for this would be called a cation because it's lost some electrons and it's positively charged. Now I remember this detail by thinking of it as positive, and that reminds me of cats, and I like cats, so cations are positive. Now in all seriousness, the thing about positive and negative ions is they attract each other. Just like opposite ends of a magnet will attract each other, oppositely charged ions will attract each other as well. The fancy word for that is electrostatic attraction. The force of attraction between the 2 ions being pulled together is the ionic bond, and that's the first type of bond we're going to learn about in chemistry. Now this is a really good spot to pause and make sure you're caught up with the notes because I'm going to move on. Now there's just one more part for ionic bonds, and that's to know what type of atoms will make ionic bonds. Going back to that fast way to know how many valence electrons are in each group, you already have this in your notes. Group 1 elements all have 1 valence electron, and so they could gain 7 valence electrons, and they would be full with a stable octet, or they could lose 1 valence electron, and the energy level under that would be full, so they'd be stable either way. The thing is, group 1 atoms would never gain 7 electrons. Losing 1 is far easier, and atoms do follow the path of least resistance if you want to think of it that way. That means all group 1 elements form a cation with a positive 1 charge. Group 2 elements, well, they could gain 6 electrons or lose 2, but the losing 2 electrons is easier, and so this group all forms cations with a positive 2 charge. Group 13 elements follow the pattern. They're all going to form 3 positive cations, but as we move to the right, group 15 elements, well, they have 5 valence electrons, and so they could gain 3 electrons, or they could lose 5. But again, path of least resistance, they're never going to lose 5 electrons, they're always going to gain 3. And so to summarize that for the notes, we're going to say that group 15 forms anions with a 3 minus charge. Now group 16, they all have 6 valence electrons, and so they're going to gain 2 electrons, so that's going to be forms 2 minus anions. And then group 17 all have 7 valence electrons, and so they're going to gain 1 electron, and that would be a 1 minus anion. Now this stair-step line on the periodic table, everything over here is a metal, and everything over on this side is a non-metal. So to make an ionic bond, you're always going to need a cation and an anion. And so that usually means that ionic bonds will form between a metal cation and a non-metal anion, because you're going to need a positively and negatively charged ion to pull themselves together. Now boron here, for example, is technically a metalloid, but it forms a +3 cation, and so the general rule is metal plus nonmetal, but sometimes it's a metalloid that stands in for a metal. Now you definitely need this concept of which kind of atoms go into an ionic bond, but it would definitely help you in this course to add this +1, +2, and -3, -2, and all that to the top of each column on your periodic table as well. You'll find a lot of uses for it in this course. Now you've reached the end of the video for this lesson. I hope it's been helpful to you today, and as always, thanks for watching.